While planets tend to take most of the spotlight in school textbooks and space agency missions, there are smaller, lesser-known worlds in our solar system that are just as fascinating. Among them are 4 extraordinary objects known as the Galilean moons, the 4 largest moons orbiting Jupiter. Despite being located so close to one another, these worlds could not be more different. One is a violent volcanic world, constantly reshaped by fire from within. Another hides beneath its icy surface what may be one of the most promising environments for life beyond Earth. There is also the largest moon in the entire solar system, a world so massive it rivals small planets. And finally, an ancient, heavily scarred moon whose surface preserves a record dating all the way back to the earliest days of the solar system itself. In this video, we will explore each of these remarkable worlds, one by one, taking a closer look at what makes them so unique. By the end, you will understand why they have become some of the most important targets for exploration. With multiple missions from both NASA and the European Space Agency planned within this decade. We begin with the innermost of these worlds, Io. To understand Io, we first need to place it in context. Jupiter is known to have 79 moons so far. A few of them orbit very close to the planet, embedded within and around its faint ring system. Beyond those lie 4 large moons known as the Galilean moons, named after Galileo, who first observed them in the year 1610. From the innermost to the outermost, they are Io, Europa, Ganymede, and Callisto. Far beyond them are the irregular moons, small and distant objects scattered much farther out in Jupiter's gravitational domain. Io orbits extremely close to Jupiter, at a distance of roughly 350,000 kilometers above the planet's cloud tops. From the surface of Io, Jupiter would dominate the sky, appearing 39 times larger than our moon appears from Earth. Io completes a full orbit in just 42.5 hours, compared to the roughly 1 month it takes our moon to orbit Earth. During its orbit, the tidal forces acting on Io are so intense that its surface is physically deformed, creating a tidal bulge that can reach up to 100 meters in height. On Earth, tidal effects caused by the moon typically shift ocean levels by only about 2 meters between high and low tide. On Io, the effect is dramatically stronger, with tidal forces reaching roughly 3 times those experienced between Earth and its moon. This constant gravitational squeezing is driven not only by Jupiter, the largest planet in the solar system, but also by the gravitational influence of the other large moons. Together, they prevent Io's orbit from becoming perfectly circular, ensuring that the tidal stress never relaxes. Io is locked in a constant cycle of stretching and compression, with no real pause. Like our moon, Io is tidally locked, meaning it rotates once per orbit. As a result, the same side of Io always faces Jupiter. And from Jupiter, only one hemisphere of Io can ever be seen. In terms of size, Io is a large moon, though it is the second smallest among the Galilean group. It is comparable in size to Earth's moon and has a similar density, suggesting a comparable level of surface gravity. However, Io stands out as the densest moon in the entire solar system. Its composition is also unusual. Unlike many large moons, which are dominated by water ice, Io is made primarily of silicate rock and iron, more similar to the terrestrial planets and our moon. In fact, Io contains the least amount of water of any known body in the solar system. Its core is likely composed of iron or iron sulfide, surrounded by a mantle and crust rich in silicate material. Unlike Earth, however, Io does not appear to generate a global magnetic field. suggesting that its core is not actively convecting. Just beneath the crust, the mantle is thought to be partially molten and at least 50 kilometers thick. This is the engine behind one of Io's most extraordinary features: its intense volcanic activity. In fact, Io is the most volcanically active world known. Before the 1970s, very little was known about Io. Early telescopic observations hinted that it lacked water and may have a surface rich in sulfur. The first spacecraft to observe Io in more detail was Pioneer 11. Although its images were limited in quality, it confirmed that Io was composed of rock rather than ice, and that it possessed a thin atmosphere. Pioneer 10 was also intended to capture close images, but its data was compromised by Jupiter's intense radiation, which was about 10,000 times stronger than the maximum radiation levels typically encountered near Earth. The real breakthrough came in the year 1979, when the Voyager 1 and Voyager 2 spacecraft flew past Jupiter. Voyager 1 passed within 20,000 kilometers of Io and revealed a world unlike any other. Its surface was covered in vivid colors, and notably, it lacked the impact craters commonly seen on other moons. Instead, it displayed towering mountains higher than Mount Everest, vast volcanic pits hundreds of kilometers across, and extensive lava flows. Most astonishingly, Voyager 1 observed plumes erupting from the surface, providing the first direct evidence of active volcanism beyond Earth. Excluding cryovolcanism, the spacecraft also confirmed that Io's surface is coated in various forms of sulfur frost, which give it its striking palette of yellows, reds, and whites. Voyager 2 observed Io a few months later from a much greater distance of about 1 million kilometers, yet it still detected several of the same volcanic plumes. This indicated that many of these volcanoes remained active over extended periods of time. Further insights came with the arrival of the Galileo spacecraft in the year 1995. Although not specifically designed to study Io in detail, Galileo captured some of the highest resolution images of its surface. Despite technical issues that limited its full capability, it observed numerous active plumes and confirmed that Io's volcanoes erupt both sulfur and silicate magma, similar to volcanic processes on Earth. Though with additional elements such as magnesium, Io's surface is a mosaic of colors and chemical activity. Yellow plains are dominated by sulfur, while white regions consist of fresh sulfur dioxide frost. Near the poles, radiation alters the surface, turning it darker and more reddish. Elsewhere, deep red deposits mark the fallout from massive volcanic plumes that rise hundreds of kilometers above the surface. One of the most prominent features is associated with the volcano Pelée, which produced a plume approximately 300 kilometers high and 1,200 kilometers wide, comparable in scale to the size of Alaska. Unlike typical volcanoes on Earth, Io's lava sources are not always located in summit depressions. Instead, many are found in vast lava lakes surrounded by high walls. One of the most notable is Loki, a massive volcanic depression about 200 kilometers in diameter. Beneath these lava lakes lies a reservoir of molten material, often covered by a thin, solid crust. Periodically, this crust collapses back into the molten interior, releasing enormous amounts of energy. Loki alone is responsible for about 1/4 of Io's total heat output. And during these collapse events, its energy release can increase up to 10 times above normal levels. Another example is the volcano Tvashtar, where observations have captured the dramatic moment when the crust sinks and exposes intensely hot lava beneath. In some images, the energy emitted is so powerful that it overwhelms the camera sensors, appearing as pure white light. In the year 2007, the New Horizons spacecraft used Jupiter for a gravity assist on its journey to Pluto. During its flyby, it turned its instruments toward Io and captured remarkable footage of Tvashtar in full eruption, with plumes rising hundreds of kilometers above the surface. Smaller eruptions were also visible across the moon, highlighting the scale and intensity of Io's ongoing geological activity. Despite its volcanic nature, Io also features towering mountains, some reaching heights of up to 18 kilometers. These mountains often stand in isolation rather than forming continuous ranges. While most are not volcanic, their proximity to lava lakes suggests that they are associated with faults and structural stresses in the crust. Another fascinating aspect of Io is its interaction with Jupiter's powerful magnetic field. As Io orbits within one of the strongest regions of this field, particles from its thin atmosphere and volcanic eruptions are stripped away and form a vast cloud of neutral particles around Jupiter. This structure, known as a neutral cloud, is one of the many ways Io continues to shape its surrounding space environment. This cloud can extend far beyond and trail behind Io's orbit. Surrounding Jupiter is another remarkable structure known as a plasma torus, a vast donut-shaped ring of ionized particles that follows the rotation of Jupiter's magnetic field. This torus moves much faster than Io itself, traveling at about 70 kilometers per second. While Io orbits at roughly 17 kilometers per second, as Io passes directly through this region, particles from the torus collide with those in the neutral cloud, energizing them and stripping electrons away. These newly ionized particles are then captured by Jupiter's magnetic field and fed back into the plasma torus. Material is continuously lost from the neutral cloud into this torus at a rate of about 1 ton per second. Over time, this process significantly enhances the scale of Jupiter's magnetic environment. If it were visible to the human eye, Jupiter's magnetosphere would appear as large in our sky as the Moon. Io's interaction with Jupiter does not stop there. As it moves through Jupiter's magnetic field lines, it generates an electric current known as the Io flux tube. This is essentially a concentrated bundle of magnetic field lines that connects Io directly to Jupiter's upper atmosphere near its poles. Similar structures are seen on the Sun between sunspots, where charged plasma flows along magnetic loops. On Jupiter, this interaction produces a bright auroral footprint, a glowing trail where Io's flux tube strikes the planet's upper atmosphere. Auroras are also visible on Io itself. But unlike those on Earth, they are not confined to the poles. Instead, they can appear across the surface, with different colors representing different elements being energized. Green light is associated with sodium, red with oxygen, and blue with sulfur. Now we move outward to Europa, one of the most intriguing worlds in the entire solar system. It is a stunning, icy moon filled with mystery. The first close-up image of Europa was captured in the year 1973 by a Pioneer spacecraft. Since then, both the Voyager and Galileo missions have studied it in greater detail. And with each observation, Europa has continued to surprise us. There is still much we do not fully understand about Europa. But piece by piece, its story is beginning to emerge. Europa is the second and smallest of the Galilean moons. Yet, it is still the sixth largest moon in the solar system, just slightly smaller than Earth's moon. With a diameter of about 3,000 kilometers, it completes an orbit around Jupiter in 3.5 days. Interestingly, Io, Europa, and Ganymede are locked in what is known as a 4:2:1 orbital resonance. This means that for every orbit Ganymede completes, Europa completes 2, and Io completes 4. This gravitational relationship prevents their orbits from becoming perfectly circular. As a result, Europa experiences constant tidal flexing as Jupiter's gravitational pull varies slightly throughout its orbit. These tidal forces stretch and compress the Moon's interior, playing a major role in shaping both its surface and what lies beneath. Europa's surface is primarily composed of water ice, giving it a bright and remarkably smooth appearance. One of its most distinctive features is the network of long, continuous fractures that stretch across the surface. These are known as lineae, thin cracks, typically 1 to 2 kilometers wide, but often extending for thousands of kilometers. While their exact origin is still uncertain, the leading theory suggests that as tidal forces pull the icy crust apart, warmer material from below rises to fill the gaps. Similar to the formation of mid-ocean ridges on Earth, scattered across the surface are small, dark features known as lenticular, each roughly 10 kilometers across. These are thought to form when warmer, less dense material rises from below, either pushing up the surface or breaking through it entirely. When this process becomes more intense, it creates chaotic regions known as chaos terrain. Areas of disrupted, broken ice surrounded by smoother plains. These regions may provide crucial clues about the structure beneath the surface. Data from the Galileo mission also suggests that Europa's equator may be covered in sharp ice formations called penitentes. These are tall, blade-like structures that can reach up to 15 meters in height, formed by direct sunlight interacting with the ice. Similar structures exist on Earth in high altitude, dry regions, though they are much smaller in scale. Despite being nearly as old as the solar system itself, Europa has very few impact craters. It has fewer than 50 large craters, compared to more than 5,000 on Earth's moon that exceed 25 kilometers in diameter. This indicates that Europa's surface is constantly being renewed. Current models estimate that its surface is only about 30 million to 180 million years old. Extremely young in geological terms. It is also the smoothest known solid surface in the entire solar system. Europa reflects a significant amount of sunlight, with an albedo of about 0.64, making it roughly 5 times brighter than our moon. However, this bright surface is constantly bombarded by intense radiation from Jupiter. The radiation levels are so extreme that a human exposed to them would receive a lethal dose within a single day. The reddish-brown streaks seen across Europa's cracks are believed to be caused by salts and sulfur compounds mixed with the ice and altered by radiation. Some studies even suggest that Europa may glow faintly in the dark, as energetic particles penetrate the surface and excite molecules beneath, causing them to emit visible light. However, this has yet to be directly observed and will likely require future missions to confirm. Europa also has a very thin atmosphere, composed primarily of oxygen. Unlike Earth, this oxygen is not produced by life, but through a process known as radiolysis, where radiation splits water molecules into hydrogen and oxygen. The lighter hydrogen escapes into space, while much of the heavier oxygen remains. Some of these particles escape as well, forming a diffuse cloud that follows Europa along its orbit around Jupiter. In the year 2012, observations from the Hubble Space Telescope revealed plumes of water vapor erupting from Europa's south pole. These plumes were estimated to reach heights of up to 200 kilometers above the surface. Later, in the year 2018, scientists revisited older Galileo data using new analysis techniques and found additional evidence supporting the existence of these plumes, strengthening the case that Europa may be actively venting material from beneath its icy crust. Studying these plumes gives scientists a remarkable advantage. It allows us to investigate what lies beneath Europa's icy surface without ever needing to land. And what may exist below that frozen shell is perhaps the most fascinating aspect of this entire world. Beneath the ice, there is very likely a global ocean, trapped between a rocky mantle below and a thick crust of water ice above. The first clues pointing to this hidden ocean came from the Voyager mission in the year 1979, and later from Galileo in the late 1990s. Between these observations, scientists detected changes in Europa's magnetic field that could only be explained if there were an electrically conductive liquid beneath the surface. The behavior of the crust provides further evidence. Europa's outer shell appears to rotate at an angle of about 80 degrees relative to its interior, something that would not be possible if the crust were rigidly attached to the mantle. Instead, it suggests that the icy shell is floating on a liquid ocean below, slowly shifting over time, completing a full rotation relative to the interior roughly once every 12,000 years. This slow movement also explains the widespread network of fractures across the surface. If the crust remained fixed, these cracks would form in specific regions. But because the surface is constantly shifting, new fractures can appear almost anywhere, creating the complex patterns we observe today. Europa orbits about 780 million kilometers from the Sun, roughly 5 times farther than Earth. As a result, sunlight there is about 25 times weaker. Very little heat reaches Europa from the Sun, leaving its surface extremely cold. Temperatures average around -160 degrees Celsius at the equator and drop to about -220 degrees Celsius near the poles. At these temperatures, the ice is as hard as granite. Yet despite this frozen exterior, Europa is not entirely cold. The intense tidal forces generated by Jupiter's gravity continuously flex the Moon, producing internal heat. This geothermal energy is thought to keep the subsurface ocean in a liquid state. The ocean likely lies beneath a crust that is about 15 to 25 kilometers thick. While the ocean itself may reach depths of 60 to 150 kilometers, what makes this even more astonishing is that Europa, though only about 1/4 the diameter of Earth, may contain more than twice as much water as all of Earth's oceans combined. And perhaps most importantly, scientists believe that this ocean is in direct contact with the rocky mantle below. This combination is critical. Life as we understand it requires 3 main ingredients: liquid water, chemical nutrients, and a source of energy. Europa appears to have all 3. The contact between water and rock could allow chemical reactions similar to those seen at hydrothermal vents on Earth's ocean floor, where entire ecosystems thrive without any sunlight. Combined with the energy provided by tidal heating, Europa becomes one of the most promising places in our solar system to search for life beyond Earth. Because of this, future missions are being designed specifically to study Europa in detail. Spacecraft will perform multiple close flybys, analyzing its surface, its atmosphere, and especially its plumes. These observations may finally help answer one of the most profound questions we can ask. Does Europa host life? Or at least the conditions necessary to sustain it? Even if life is not found, these missions will still transform our understanding of icy worlds and the processes that shape them. Europa is not just another moon. It is a window into environments that may exist across the universe. Now we move on to Ganymede, the third of Jupiter's Galilean moons and the largest moon in the entire solar system. It is also home to the largest known ocean beyond Earth. But Ganymede holds another mystery, something hidden deep beneath its surface that sets it apart from every other moon we have studied. Among Jupiter's 79 known moons, Ganymede stands as the largest of the Galilean group, with a diameter of about 5,268 kilometers. For comparison, that is about 0.41 times the diameter of Earth and slightly larger than Triton, Saturn's largest moon, which was once thought to hold the record. Ganymede is even larger in volume than the planet Mercury, though it contains less mass. Its average density is about 1.9 grams per cubic centimeter, compared to Mercury's much higher density. reflecting a very different composition. Like Europa, Ganymede has a thick outer shell of water ice, extending down roughly 150 kilometers. Beneath this crust lies a vast ocean of liquid water, and this ocean is enormous. It is estimated to be about 100 kilometers deep on average, making it roughly 10 times deeper than the deepest parts of Earth's oceans. In total, Ganymede may contain more water than all of Earth's oceans combined. This abundance of water means that Ganymede is composed of roughly half rock and half water, with smaller amounts of metals and other ices. Its name comes from ancient mythology, where Ganymede was taken by Jupiter to serve as a cupbearer for the gods. In a way, the Moon lives up to that name, carrying vast reservoirs of water around its parent planet. Ganymede also has a very thin atmosphere containing oxygen. At first glance, this might suggest the possibility of life. However, the conditions are far from ideal. The atmosphere is extremely tenuous, with pressures many billions of times lower than Earth's at sea level, making it impossible for humans to breathe. There is another challenge as well. The ocean beneath Ganymede's surface is so deep that the immense pressure at its lower layers may compress water into a form of high-pressure ice. On Earth, life can thrive in deep ocean environments because minerals are supplied by hydrothermal vents on the seafloor. But on Ganymede, a thick layer of ice may separate the ocean from the rocky core, preventing these crucial interactions. That said, there is still uncertainty. If the ocean contains enough salt, it could alter the internal structure, potentially creating multiple layers of liquid water separated by ice. In such a scenario, the deepest layers might still come into contact with the rocky mantle, increasing the chances that life could exist there. But perhaps the most surprising feature of Ganymede lies even deeper. Somehow, this moon generates its own magnetic field. This discovery was made in the year 1996, when the Galileo spacecraft performed a series of flybys. One of the key indicators was the detection of auroras within Ganymede's thin atmosphere. Further observations revealed that these auroras behaved in unexpected ways. They did not shift as much as they should have under Jupiter's influence. This led scientists to propose that a salty, electrically conductive ocean beneath the surface interacts with the magnetic field, creating a kind of magnetic friction that stabilizes these auroral patterns. A magnetic field is a crucial feature for any world. On Earth, it protects the surface from harmful radiation, allowing life to flourish. Ganymede's magnetic field, however, is not strong enough to fully shield it, especially since it exists within Jupiter's powerful radiation environment. The surface still receives significant radiation exposure, enough to make conditions extremely hazardous over extended periods of time. However, conditions on Ganymede are still far less extreme than on the moons that orbit closer to Jupiter. And yet, one question remains unresolved. Why does Ganymede have a magnetic field at all? On Earth, our magnetic field is generated by a hot, molten core. Convection currents within this liquid metal move charged particles, creating the magnetic field that surrounds and protects our planet. But on Ganymede, this process should not be happening. The Moon is smaller than Earth, and based on its size and composition, scientists believe its core should have cooled long ago, becoming solid. If that were the case, convection would stop, and with it, the magnetic field should disappear. Yet it has not. In fact, Ganymede is the only moon in the entire solar system known to possess its own magnetic field. None of Jupiter's other moons have one. So what is happening here? One possible explanation lies in Ganymede's relationship with Jupiter and its neighboring moons. Through a process known as tidal heating, Ganymede orbits Jupiter roughly once every 7 days. and its orbit is slightly elliptical. This means that sometimes it is closer to Jupiter, and at other times farther away. As it moves through these varying distances, the strength of Jupiter's gravity changes, stretching and compressing the Moon over and over again. If you have ever taken a piece of soft material and repeatedly stretched and compressed it, you may have noticed that it begins to warm up. This happens because of internal friction. On the scale of a moon, this same process generates heat, and it is known as tidal heating. This effect is amplified by what is called the Laplace resonance, a precise orbital relationship between Ganymede, Europa, and Io. For every orbit Ganymede completes, Europa orbits twice, and Io orbits 4 times. This configuration is not random. It is the result of gravitational interactions that have locked the system into a stable pattern. But it also means that Ganymede is constantly being pulled not just by Jupiter, but by its neighboring moons as well. All of this creates continuous internal stress. And it is possible that this stress generates enough heat to keep part of Ganymede's core from fully solidifying. If that is the case, it could allow convection to continue, sustaining the magnetic field. Scientists are not yet certain, but this remains one of the leading ideas. The effects of these processes can also be seen on Ganymede's surface. It is divided into 2 distinct regions. Darker areas cover about 1/3 of the surface, while lighter regions make up the remaining 2/3. By studying the number of impact craters, scientists have determined that the darker regions are older as they contain more craters. The lighter regions are younger, though still ancient, and are marked by long ridges and grooves that can reach heights of up to 700 meters and stretch for thousands of kilometers. How these Vishal structures formed is still unclear. One theory suggests that tidal forces stretched and reshaped the crust during a more active period in Ganymede's history. If so, these same forces may also have contributed to heating the interior and preserving its magnetic field. Ganymede's magnetosphere has proven to be an incredibly valuable tool for scientists. By studying how auroras behave in its thin atmosphere, researchers were able to confirm the presence of a subsurface ocean, all without ever landing on the Moon. As for the rest of Ganymede's mysteries, future missions may provide answers. A spacecraft is planned to explore Jupiter and its icy moons in greater detail, including Ganymede itself. It will take many years to arrive, but when it does, it may finally reveal what lies beneath the surface of this remarkable world. Until then, Ganymede remains a place where known physics meets unanswered questions. Now we move outward to Callisto. Despite being one of the largest moons in the solar system, many people know surprisingly little about it. At first glance, it might seem like a quiet and uneventful world, but in reality, Callisto tells a very different story. Callisto is the 3rd largest moon in the solar system and only slightly smaller than the planet Mercury, with a diameter of about 4,820 kilometers. However, while its size is comparable, its mass is only about 1/3 of Mercury's, meaning it is far less dense and has much weaker gravity. It is the 2nd largest of the Galilean moons and orbits much farther from Jupiter than the others, taking about 17 Earth days to complete a single orbit at a distance of roughly 1.9 million kilometers. Even at this distance, Callisto is tidally locked, always showing the same face to Jupiter. However, unlike Io, Europa, and Ganymede, it is not part of any orbital resonance with the other moons. This isolation has had a profound effect on its evolution. Callisto has an extremely thin atmosphere, composed mainly of carbon dioxide and possibly small amounts of oxygen. It is so tenuous that the particles rarely collide with one another. In theory, Such an atmosphere should be stripped away relatively quickly, within just a few years. But evidence suggests that Callisto's surface may be replenishing these gases through the slow release of carbon dioxide from surface ice. The most striking feature of Callisto is its surface. It is one of the oldest known in the entire solar system, with an age of over 4 billion years. The surface is densely covered with impact craters of all sizes, more so than any other object we have observed. It is so heavily cratered that it has reached what scientists call saturation, where new impacts simply overlap older ones. Unlike Earth or other geologically active worlds, Callisto shows no signs of processes such as volcanism or tectonic activity that could reshape its surface. On Earth, erosion, water, plate movement, and even biological activity constantly renew the landscape, erasing evidence of past impacts. Even moons like Europa and Io experience internal activity driven by tidal forces. But Callisto does not, because it is not significantly affected by tidal heating. It lacks the internal energy needed to drive geological change. As a result, its surface has remained largely unchanged for billions of years, preserving a record of the early solar system. Another unusual consequence of this inactivity is the absence of large pervert ranges. Callisto's surface is relatively flat, shaped primarily by impacts rather than internal forces. It is thought that when Callisto first formed, it may have been an ocean world that later froze over. Since then, apart from constant meteor bombardment, very little has altered its appearance. Callisto has remained almost unchanged for billions of years. Its surface is a frozen record of the early solar system, and some of its impact craters are truly extraordinary. One of the most impressive is Asgard, the second largest impact structure on Callisto, stretching about 1,600 kilometers across. Even more remarkable is Valhalla, the largest multi-ring impact crater in the entire solar system, with a diameter of roughly 3,800 kilometers. These enormous structures give Callisto its distinctive appearance. Many of them feature multiple concentric rings, more than seen on almost any other world. The impacts that formed these basins were so powerful that they may have completely penetrated the Moon's outer crust, which later refroze. The lighter regions at the center of these craters are believed to be the result of this refreezing process. If we look closer at these central regions, we see a mottled landscape, where bright elevated areas contrast sharply with darker, smoother plains. These regions contain far fewer craters than the surrounding terrain, suggesting they are significantly younger, possibly about 2 billion years younger than the rest of Callisto's surface. The rings themselves are thought to be fractures in the crust, formed as the surface failed and collapsed in concentric patterns following the immense impact. Within these rings, small bright features, known as knobs, can still be seen. These are believed to be the eroded remnants of ancient crater rims. Over time, processes such as micrometeorite impacts or the slow sublimation of ice may have worn them down. The reason they appear brighter is likely because darker debris has gradually fallen away, exposing cleaner ice beneath. Even smaller craters on Callisto have unusual characteristics. Compared to similar features on our Moon, they tend to be much shallower. For example, one large impact structure spans well over 100 kilometers in width, yet is only about 600 meters deep. This could be due to the impactor breaking apart before striking the surface, spreading out the energy. Alternatively, later, geological adjustments may have softened and leveled the terrain over time. Despite being more than 1 billion years old, many of these craters still preserve clear ejecta patterns, further evidence of how little Callisto has changed. Some craters display even stranger formations. Instead of having a central peak, as is common on many planetary bodies, Certain large craters on Callisto contain central pits. This unusual structure may be linked to the composition and thickness of the crust, which is thought to be relatively thin and underlain by softer material, possibly ice or even a subsurface ocean. Estimates suggest the crust could be between 80 and 150 kilometers thick. Observations from spacecraft studying Jupiter revealed something intriguing. Jupiter's magnetic field does not pass cleanly through Callisto, suggesting the presence of a conductive layer beneath the surface, likely at least 10 kilometers thick. This would be difficult to explain unless part of the interior is either partially molten or contains liquid with enough variation in temperature to conduct electricity. There is also evidence that Callisto may have a small silicate core, with a radius of about 600 kilometers. This raises an important question. Could Callisto support life in the same way as other icy worlds? For life as we understand it, two key ingredients are required: liquid water and a source of energy. Callisto may possess liquid water beneath its surface, but it receives very little heat from the sun, being located about 800 million kilometers away. Unlike Europa or Io, it is not significantly affected by tidal heating, meaning internal energy sources are limited. Radioactive decay may provide some warmth, but likely not enough to create a dynamic environment. There is also a practical challenge. On moons like Europa or Enceladus, plumes eject material from beneath the surface, allowing scientists to study their internal oceans without drilling. Callisto shows no evidence of such activity. To directly investigate its interior, a mission would likely need to penetrate the thick crust, which is a far more difficult task. For these reasons, Callisto is considered a less promising candidate for life compared to other icy moons. However, that does not make it unimportant. In fact, Callisto may be one of the most suitable locations for future human exploration in the outer solar system. Because it orbits far from Jupiter, at a distance of about 1.9 million kilometers, it lies outside the planet's most intense radiation belt. This makes its environment far safer compared to the inner moons. Callisto also contains abundant water ice, which could be used for fuel production and life support. By separating hydrogen and oxygen, it could provide both rocket propellant and breathable air. Its geological stability is another advantage. With little to no tectonic or volcanic activity, the surface would be a relatively stable place to build structures. The lack of extreme terrain, such as towering mountains or deep trenches, would also make travel and infrastructure development easier. From Callisto, missions could safely explore the inner regions of the Jovian system or use it as a stepping stone for journeys deeper into the outer solar system. Its low gravity would make launching spacecraft more efficient, and flybys of Jupiter could provide powerful gravitational assists for further travel. While this remains a vision for the future, it is a realistic one if humanity continues to expand into space. Although past missions have provided valuable data, there is still much we do not know about Callisto. Future spacecraft are expected to perform multiple close flybys, helping to answer key questions. Does Callisto truly have a subsurface ocean? And if so, could it support even the most basic forms of life? Beyond those questions lie others we have not yet thought to ask. Callisto remains a quiet world, but one filled with untold stories waiting to be uncovered. And with that, we have explored the 4 great Galilean moons of Jupiter, each one a world entirely different from the others. Now, far beyond Jupiter, orbiting the ringed giant Saturn, lies another icy world filled with mystery. This is Rhea, the second largest moon of Saturn. Though often overshadowed by its larger neighbor Triton, Rhea is a fascinating place in its own right. Towering ice cliffs rise hundreds of meters high. Its internal structure challenges current scientific models, and it holds one of the most puzzling discoveries in planetary science. It is time for this lesser-known moon to step out from the shadow of its giant sibling. Let us journey onward, deeper into the Saturnian system, and uncover what makes Rhea such an extraordinary world. Rhea was discovered on the 23rd of December in the year 1672 by Giovanni Domenico Cassini, the Italian astronomer who made major contributions to our understanding of Saturn and its moons. Named after the Titan goddess Rhea from Greek mythology, this icy world has fascinated scientists for centuries. Rhea is the second largest moon of Saturn, after the much larger Titan, with a diameter of about 1,528 kilometers. That makes it roughly half the size of our own moon. If placed on Earth, it would stretch across a distance comparable to traveling from London to Warsaw. Rhea orbits Saturn at about 527,000 kilometers and completes one full orbit in roughly 4.5 Earth days. Like many large moons, it is tidally locked, always showing the same face to its parent planet. Its surface is one of the most reflective in the entire solar system, with an albedo of about 0.7, meaning it reflects around 70% of the sunlight that reaches it. This is due to its composition, which is dominated by water ice. But this bright appearance hides a violent past. The surface is heavily cratered, telling the story of countless impacts over billions of years. One of the largest craters, known as Mamaldi, spans about 480 kilometers in diameter, comparable to the distance between major European cities. These craters are more than just scars. They offer a glimpse into the moon's interior. Observations show that the floors of some craters appear darker than their surroundings, suggesting that impacts have excavated material from beneath the surface, possibly exposing darker, less reflective ice or impact melt. Another striking feature of Rhea is the presence of bright, wispy streaks that stretch across its surface. These were first observed by spacecraft in the early 1980s, but their true nature remained unclear for decades. Later, higher resolution images revealed that these streaks are actually massive ice cliffs, some rising hundreds of meters high. They likely formed when the icy crust fractured in the distant past, with sections being pushed upward through tectonic processes. These features provide important clues about Rhea's geological history and the forces that shaped it. In the year 2010, data from a spacecraft studying Saturn revealed something unexpected. Rhea appeared to have a very thin atmosphere, or more precisely, an exosphere. While extremely tenuous, it was still measurable. This atmosphere consists mainly of oxygen and carbon dioxide, with the oxygen being trillions of times less dense than Earth's atmosphere at sea level. The origin of this atmosphere is likely linked to radiation. Charged particles from Saturn's magnetosphere strike the icy surface, breaking apart water molecules and releasing oxygen. At the same time, carbon dioxide may form through chemical reactions involving organic materials on the surface. This discovery placed Rhea among the very few moons known to possess an oxygen-rich exosphere, alongside worlds like Europa and Ganymede. Beneath the surface, Rhea holds even more mysteries. Based on its average density of about 1.2 grams per cubic centimeter, scientists believe it is composed mostly of water ice, around 75%, with the remaining 25% made up of rock. This has led to it being described as a kind of frozen, dirty snowball. Unlike larger moons that have clearly separated internal layers, Rhea is thought to be relatively uniform throughout, with only a modest core. However, some studies have suggested the possibility of a subsurface ocean. While this idea remains uncertain and less supported than similar hypotheses for moons like Europa or Enceladus, it remains an intriguing possibility that future missions may investigate. Another puzzle lies in Rhea's shape. Instead of being a perfect sphere, it is slightly flattened at the poles and bulges at the equator, forming what is known as a triaxial ellipsoid. What makes this unusual is that its shape does not fully match what would be expected based on its rotation. This has led to the suggestion that its internal structure may not be evenly distributed, with denser material located away from the center. Much of what we know about Rhea comes from a long-running mission that explored the Saturn system for over a decade. During several close flybys, spacecraft passed just tens of kilometers above the surface, capturing detailed images and collecting valuable data. These observations confirmed that Rhea does not possess a global magnetic field. The surface was revealed to consist of two main types of terrain. There are heavily cratered regions, extremely old and dating back to the early solar system, and smoother plains that appear younger. These smoother areas may have formed when material from large impacts was ejected and later settled back onto the surface, covering older craters and creating more even terrain. One of the most intriguing findings, however, came not from what was discovered, but from what was not. Earlier measurements had suggested that Rhea might possess a system of rings, but despite careful observation during close flybys, no such rings were found. While this does not entirely rule out the existence of a faint debris disk, it showed that Rhea is not surrounded by the kind of ring system once imagined, but it does make it much less likely. Another intriguing aspect of Rhea is its place within Saturn's complex system of moons. Rhea orbits Saturn inside what is known as the E-ring, a diffuse ring of ice particles thought to be supplied by cryovolcanic eruptions from Enceladus. While Rhea itself does not appear to be geologically active like Enceladus, its position within this ring means it is constantly interacting with these icy particles. Even though it lies near the outer regions of the E-ring, where the density is lower, over long periods of time this interaction may subtly affect the surface, contributing to its bright, reflective appearance. As we reflect on what we have learned about Rhea, it becomes clear that this moon, often overshadowed by its more famous neighbors, is a fascinating world in its own right. From its heavily cratered hemisphere to its relatively smoother terrain, from its extremely thin atmosphere to its role within Saturn's system, Rhea continues to intrigue scientists and spark our imagination. And yet, our exploration of this moon is far from complete. Many questions remain unanswered. What is the exact nature of its interior? How has it evolved over billions of years? And could it possibly harbor a subsurface ocean capable of supporting simple forms of life? These questions remain open, awaiting future exploration of the Saturnian system, where Rhea will likely be observed again. As we step back and consider the broader picture, the diversity of worlds in our solar system becomes even more striking. From the scorching surface of Venus to the frozen plains of Pluto, from the towering volcanoes of Mars to the hidden oceans beneath icy moons like Enceladus, our cosmic neighborhood is filled with worlds waiting to be understood. Rhea, quietly reflecting distant sunlight, stands as a reminder of how much there is still to discover. And then there is Triton, Saturn's largest moon, and one of the most extraordinary places in the entire solar system. It is the only moon with a thick, substantial atmosphere, and one of the very few places beyond Earth where stable liquids exist on the surface. Triton is the sixth largest spherical moon orbiting Saturn, and unlike the Galilean moons of Jupiter, it stands almost alone in its size. With the rest of Saturn's moons being significantly smaller, Triton's diameter is about 50% larger than Earth's moon, and it is roughly 80% more massive. In fact, it is the second largest moon in the solar system, just behind Ganymede. Despite sometimes appearing slightly larger due to its thick atmosphere, Triton's true size is still larger than the planet Mercury, although it is only about 40% as massive due to its relatively low density. Its surface gravity is weak, around 0.14 times that of Earth, or approximately 1.35 meters per second squared. Even lower than the gravity on our own moon. This low density suggests that Titan is composed of roughly equal parts water ice and rocky material. Like many large celestial bodies, it is believed to have a differentiated interior, meaning it has distinct layers. Beneath its outer crust, there is likely a subsurface ocean made of water mixed with ammonia, kept in a liquid state by internal heat, pressure, and tidal forces. Evidence for this internal ocean became stronger when the Cassini spacecraft detected extremely low-frequency radio signals interacting with Titan's environment. The surface itself does not reflect these signals well, but a liquid layer beneath could explain the observations. In addition, surface features appear to have shifted by up to 30 kilometers over time, suggesting that the crust may be floating above this internal ocean rather than being rigidly connected to the core. While no direct evidence of life has been found, scientists speculate that such an environment could potentially support simple forms of life. Titan does not generate its own magnetic field, but it remains largely protected from the solar wind because about 95% of its orbit lies within Saturn's magnetosphere. It orbits Saturn once every 15 days and 22 hours, following a slightly elliptical path. Like many moons, Titan is tidally locked, meaning it always shows the same face to Saturn. Its thick atmosphere completely obscures the surface from space, though from the ground, Saturn would appear fixed in the sky, never rising or setting. What truly sets Titan apart, however, is its atmosphere. Unlike Earth, where the atmosphere forms a relatively thin layer around the planet, Titan's atmosphere extends far into space, forming a dense, hazy envelope. Although Titan is smaller than Earth, its atmosphere is about 1.9 times more massive, and roughly 7 times more massive when measured per unit surface area. Its weaker gravity allows this atmosphere to extend much farther outward, creating a thick, almost blanket-like appearance. The pressure at Titan's surface is about 1.45 times that of Earth, meaning it is 45% higher than what we experience at sea level. Its atmosphere stretches up to around 600 kilometers, far beyond Earth's mesosphere, which ends at about 120 kilometers. Even at distances close to 1,000 kilometers, spacecraft like Cassini experienced measurable atmospheric drag, requiring adjustments to maintain stable orbits. Like Venus, Titan is also a superrotator, meaning its atmosphere moves faster than the Moon itself rotates, creating complex and dynamic weather patterns high above its hidden surface. This can be seen most clearly at the poles of Titan, where each pole hosts a powerful polar vortex rotating once every 9 hours, compared to the Moon's own rotation of 16 days. These vortexes behave like permanent hurricanes, constantly spinning in Titan's upper atmosphere. So what exactly is this atmosphere made of? And why does it appear orange? The answer lies in its composition. Around 98.4% of Titan's atmosphere is nitrogen, with most of the remaining portion made up of methane, along with small amounts of hydrogen. There are also trace hydrocarbons formed when ultraviolet light breaks down methane in the upper atmosphere. And it is these complex hydrocarbons that give Titan its distinctive orange color. This continuous breakdown of methane presents a mystery. Over time, Titan should have run out of methane in roughly 50 million years, which is extremely short compared to the age of the solar system. This suggests that there must be an active source replenishing it, most likely cryovolcanoes. Although the possibility of biological processes has not been completely ruled out, methane in the atmosphere also creates a greenhouse effect, helping to warm the surface. But at the same time, Titan's thick haze reflects much of the sunlight, producing an anti-greenhouse effect that offsets some of that warming. Because Titan is so far from the Sun, its upper atmosphere receives only about 1% of the sunlight that Earth does. And by the time that light reaches the surface, only about 0.1% remains. The lighting conditions are extremely dim, similar to standing on an asphalt parking lot at dusk. Despite this, a human standing on Titan would not need a pressure suit. Only an oxygen supply and extremely warm clothing to remain comfortable. Titan is incredibly cold, with an average temperature of -180 degrees Celsius. At these temperatures, water remains permanently frozen, unable to melt, evaporate, or sublimate. Instead of water clouds, Titan has methane clouds, and under the right conditions, methane can exist as a liquid. Methane freezes at -182.5 degrees Celsius and boils at -161.5 degrees Celsius. Meaning, Titan's temperature and pressure allow methane to cycle between gas, liquid, and solid. This led scientists to predict the existence of lakes and seas of liquid hydrocarbons on Titan, something never before observed beyond Earth. To explore this possibility, the Huygens probe was sent into Titan's atmosphere. After a descent lasting nearly 3 hours, it successfully landed on the surface. While it did not find active lakes at its landing site, it did discover evidence of a dried lakebed. The surface was covered in rounded stones, similar to pebbles shaped by flowing liquid on Earth, suggesting that liquid methane had once been present. Later observations from the Cassini spacecraft confirmed that methane lakes still exist, particularly near Titan's poles. One of these, Ontario Lacus, covers about 15,000 square kilometers and shows clear signs of shoreline erosion and river channels feeding into it. This indicates that liquid hydrocarbons flow across Titan's surface in a cycle similar to water on Earth. Ontario Lacus is relatively shallow, ranging from around 40 centimeters to 3 meters deep, with its deepest point just over 7 meters. Its surface is remarkably smooth, with waves no larger than a few millimeters, making it appear like a mirror. Further exploration revealed even larger bodies of liquid. Jingpo Lacus showed sunlight reflecting directly back into space, confirming the presence of liquid. Even more impressive is Ligeia Mare, a vast sea in the northern hemisphere with a surface area of about 126,000 square kilometers. Larger than Lake Superior on Earth, it has an average depth of around 50 meters, with some areas exceeding 200 meters, and is fed by multiple river systems. The largest of all is Kraken Mare, spanning roughly 400,000 square kilometers. This enormous sea is divided into 2 main regions connected by a narrow channel, where tidal forces may create strong currents and even whirlpools. Its depth reaches up to around 170 meters, making it one of the most significant liquid bodies in the solar system outside Earth. Titan's surface itself is surprisingly young, estimated to be around 100 million years old, which suggests ongoing geological activity. One of the main drivers of this activity is believed to be cryovolcanism. Instead of molten rock, Titan's volcanoes erupt a mixture of water and ammonia. When this material reaches the surface, it freezes, gradually reshaping the landscape. Because this icy mixture is less viscous than lava on Earth, it spreads more easily, forming broad, low features rather than tall volcanic mountains. One possible cryovolcano, known as Sotra Patera, features a deep pit approximately 1.7 kilometers deep, indicating powerful eruptions in the past. Although it does not appear active today, it remains a strong candidate for ongoing geological processes. The surface of Titan, composed of this icy mixture, has been described as similar to damp sand or soft snow with a thin crust, based on how the Huygens probe behaved upon landing. If you are careful, you can walk across Titan's surface without too much trouble. But if you step too hard, you may sink deeply into it. Scientists believe Titan's ground behaves somewhat like compacted snow or damp sand, with a thin crust covering softer material beneath. Titan's highest mountains appear as long ridge belts, similar to the Rocky Mountains on Earth. And these formations may even be linked to cryovolcanic activity. The tallest known peak, located in the Mithrim Montes range, rises to about 3,337 meters. At these altitudes, it is thought that methane snow may settle on the peaks, creating a landscape unlike anything found on Earth. Across Titan's surface, there are also vast gorges, valleys, and dune fields. Using infrared imaging to penetrate the thick haze, scientists have identified large regions of dark terrain. At first, these areas were believed to be seas. But when the Huygens probe landed in a region called Shangri-La, it revealed something different. These dark plains are composed of fine, organic-rich material shaped by wind into dune systems, similar to deserts on Earth, such as the Namib. It is possible that these regions were once liquid seas, but today they exist as dry, windswept landscapes. In many ways, Titan can be compared to a much colder version of early Earth. Its chemistry, atmosphere, and surface processes suggest conditions that may resemble those that existed on our planet billions of years ago. Despite all that we have learned, Titan remains one of the most fascinating worlds in the solar system, and future exploration will likely reveal even more about its secrets. Cassini's mission around Saturn lasted 13 years and provided an enormous amount of data that scientists are still analyzing today. One of its most important discoveries was confirming the existence of stable liquid methane lakes on Titan. However, discovering these lakes raised a new question. How did they form? Unlike Earth, where water shapes the landscape, Titan operates on a methane cycle. Methane clouds form in the atmosphere, condense, and fall as rain onto the surface, carving channels and river systems that flow into lakes and seas. Radar observations from Cassini revealed extensive river networks and valleys shaped by flowing methane. Some of the most striking features are found near Ligeia Mare, where large canyon systems known as vidflumina cut deep into the surface. These canyons have steep walls hundreds of meters high and may represent ancient river valleys that have since been flooded as liquid levels changed over time. In some places, liquid methane still fills these channels, though it is not always actively flowing. The lakes and seas on Titan can reach enormous sizes. Krakenmare, the largest known sea, spans around 400,000 square kilometers, making it larger than the Caspian Sea on Earth. While many lakes are relatively shallow, only a few meters deep, some regions can reach depths of over 200 meters. In total, the amount of hydrocarbons on Titan is estimated to be more than 300 times greater than all known fossil fuel reserves on Earth. Interestingly, many of Titan's lakes appear almost perfectly smooth. In some observations, wave heights are less than 1 millimeter, giving the surface a mirror-like appearance. This was unexpected, as Titan's dense atmosphere and low gravity should allow for larger waves. Possible explanations include extremely calm wind conditions, higher than expected liquid viscosity, partial freezing, or even a thin layer of aerosols forming a film across the surface that suppresses wave formation. The discovery of these lakes would not have been possible without Cassini's advanced instruments. Radar mapping first identified dark regions on Titan's surface, and infrared imaging later confirmed them as liquid bodies by detecting sunlight reflecting off their surfaces. This process, known as specular reflection, allowed scientists to distinguish between solid terrain and liquid lakes. In some cases, changes over time were observed, where previously dry regions became darker, suggesting the formation of new shallow lakes after rainfall events. One final detail stands out. Titan's lakes are not evenly distributed across the surface. Instead, the vast majority of them are concentrated near the poles, where temperatures and atmospheric conditions allow methane to accumulate and remain stable over long periods of time. However, the Huygens probe, which was part of the Cassini mission and landed near Titan's equator, did observe flow channels in these regions as well. This raises an important question if rivers exist near the equator. Where are the lakes they should flow into? The answer likely lies in Titan's seasonal cycles. Similar to Earth, Titan experiences long seasonal changes, and during certain periods of its year, rainfall can occur near the equator, temporarily forming surface liquids. Over time, these liquids likely evaporate and migrate toward the poles, where they accumulate and form the lakes observed by Cassini and Huygens. Even though Cassini spent 13 years orbiting Saturn, that is less than half of a full Saturnian year, which lasts about 30 Earth years, meaning we have only seen part of Titan's seasonal behavior. It is likely that lake levels change over time, with some lakes even drying up completely before reforming. Another mystery revealed by Cassini data involves the shape of some of Titan's smaller lakes. Unlike lakes on Earth, which usually form through erosion and have smooth, shallow edges, some of Titan's lakes are surrounded by steep, elevated rims. This unusual structure suggests a very different origin. Scientists now believe that these lakes may have formed from explosive events beneath the surface. In the past, Titan may have been even colder, with nitrogen rain and snow dominating instead of methane. Liquid nitrogen could have seeped into the crust, forming underground reservoirs. As methane gradually accumulated in the atmosphere and warmed the environment, this trapped nitrogen would begin to evaporate, expanding and building pressure beneath the surface until it eventually erupted, creating explosion craters. Over time, these craters filled with liquid methane, forming the lakes we observe today. Despite everything Cassini has revealed, there is still much to learn. The lakes of Titan represent only a small part of the data collected, and scientists will continue studying this information for many years, gradually building a clearer understanding of the entire Saturnian system. There is still so much waiting to be discovered. And then we turn to another extraordinary world, Enceladus. At first glance, it may seem small and unremarkable, but it is one of the most intriguing objects in the entire solar system. Beneath its bright, icy surface lies a world of active geology and hidden oceans. Thanks to the Cassini mission, we have been able to study Enceladus in remarkable detail. And in many ways, we understand it better than some larger moons. Yet, despite all we have seen, its interior remains one of the greatest mysteries. Enceladus is currently the 14th closest moon to Saturn. Although that classification may change as more small moonlets are discovered within Saturn's rings, it is the second closest major moon, orbiting just beyond the main ring system, and it completes one orbit around Saturn in about 33 hours. Interestingly, it is locked in a 2-to-1 orbital resonance with the moon Dione, meaning it orbits Saturn twice, for every one orbit of Dione. This gravitational interaction prevents its orbit from becoming perfectly circular and causes tidal deformation, which generates internal heat. This heating is crucial. Enceladus appears to be composed mostly of clean water ice, with very little rocky material on its surface. Because Saturn is so far from the Sun, the outer layers of this water have frozen solid, turning the Moon into a vast, icy world. In fact, Enceladus is one of the most reflective objects in the solar system, with a bond albedo of about 0.81, similar to fresh snow. As a result, it reflects most of the sunlight it receives, making it extremely cold, with surface temperatures around -200 degrees Celsius. However, beneath the surface, conditions are very different. At depths of around 30 to 40 kilometers, pressure and tidal heating increase the temperature enough for water to exist in liquid form. This suggests the presence of a subsurface ocean, possibly even a global ocean beneath the icy crust, similar in concept to the molten mantle beneath Earth's surface. At the very least, scientists believe there is a large reservoir of liquid water beneath the South Pole. The strongest evidence for this comes from the massive plumes of water vapor erupting from fractures in the surface, a process known as cryovolcanism. These jets are incredibly powerful, ejecting around 250 kilograms of water every second at speeds exceeding 2,000 kilometers per hour. Much of this material escapes Enceladus's weak gravity and enters orbit around Saturn, contributing to the formation of the E-ring. This ring is vast and diffuse, extending roughly 2,000 kilometers in width, and is best seen when backlit by the sun. Under these conditions, the tiny ice particles scatter light in a way that gives the ring a striking blue appearance, making it one of the bluest structures in the entire solar system. Even more so than Neptune, the shape of the ring is also influenced by Enceladus itself, as the continuous outflow of material creates delicate, stream-like patterns within the ring, constantly reshaped by the Moon's activity. As Enceladus moves along its orbit, the denser structures within the E-ring gradually smooth out. During the Cassini mission, the spacecraft was able to fly directly through the plumes erupting from Enceladus, allowing scientists to analyze their composition. This was not part of the original mission design, as the plumes were only discovered after Cassini arrived. However, the spacecraft carried an instrument known as the Cosmic Dust Analyzer, which was originally intended to study dust particles around Saturn, and it proved invaluable for sampling material from the plumes. Although the instrument was not specifically optimized for this purpose, it still provided remarkable insights. Water was the dominant substance detected, but alongside it, scientists also found carbon dioxide, nitrogen, methane, and even amino acids. These molecules are particularly significant because amino acids are the building blocks of life and are commonly found around hydrothermal vents on Earth's ocean floors. This raises an important question: could similar hydrothermal systems exist beneath the surface of Enceladus? And if so, could they support life? While there is strong evidence for a subsurface ocean, the exact internal structure of Enceladus is still not fully understood. Earlier models suggested that the Moon might be composed almost entirely of water ice, but data from Cassini indicates that its mass is greater than expected, implying the presence of a denser core made of rock or silicate material. Scientists now favor the idea that Enceladus has a differentiated interior, with distinct layers, including a rocky core, a liquid ocean, and an icy crust. This is particularly interesting because Enceladus is relatively small, only about 500 kilometers in diameter, placing it near the threshold where an object becomes spherical due to its own gravity. Many bodies of similar or smaller size do not achieve this state. If Enceladus does indeed have a rocky core, this would be crucial for the existence of hydrothermal vents, as such systems require interaction between liquid water and rock. A rocky ocean floor would also provide essential minerals and nutrients that could support the development of life. Cassini also mapped thermal emissions across Enceladus and found that the heat was concentrated along features known as the tiger stripes. These are large fractures near the South Pole, each roughly 130 kilometers long, about 2 kilometers wide, and around 500 meters deep. These fractures are believed to be tectonic in nature, acting as pathways through which subsurface water escapes into space. One of the most striking features of Enceladus is the relative absence of impact craters, especially in the southern hemisphere. This suggests that the surface is geologically young. Although Enceladus has a thin atmosphere formed from its own plumes, it is not dense enough to burn up incoming meteoroids. Instead, the continuous deposition of fresh ice from the plumes gradually smooths over the surface, erasing older features and contributing to the Moon's nearly perfect spherical shape. Topographically, Enceladus is relatively smooth, with few large mountains or major variations in elevation. However, near the South Pole, the terrain becomes more rugged and fractured. High-resolution images reveal a landscape that resembles a vast frozen glacier, with a mix of smooth, icy plains and jagged, broken regions. In contrast, the northern hemisphere shows a much higher number of impact craters, indicating that it is significantly older and less active than the south. As Cassini flew close to the surface, it captured detailed images of the tiger stripe region, revealing a landscape unlike anything on Earth. The ice appears folded, compressed, and fractured, forming intricate patterns shaped by internal forces. The fact that we were able to observe such detail from a distant moon is remarkable. However, since the end of the Cassini mission, we no longer have a spacecraft orbiting Saturn to continue this level of study. There have been several proposals for future missions to Enceladus, including ideas for probes that could sample the plumes more directly or even attempt to reach the subsurface ocean. One confirmed mission, Dragonfly, will explore Titan, but it will not investigate Enceladus. As a result, it may still be decades before we return to this moon, leaving many of its mysteries unresolved. And yet, Enceladus remains one of the most compelling places in the search for life beyond Earth. Beneath its icy crust, hidden from view, there may exist an ocean filled with chemical energy, warmth, and the ingredients necessary for life. Now imagine a completely different world. You are standing at the edge of the tallest known cliff in the solar system. Verona Hoop is on Miranda, a moon of Uranus. The drop stretches for about 20 kilometers, roughly 16 times taller than the highest cliff on Earth, Mount Thor, which stands at around 1,250 meters. But Miranda is a small moon, only about 470 kilometers across, with extremely weak gravity. On Earth, gravity pulls you downward at 9.8 meters per second squared. On our moon, that drops to about 1.6. But on Miranda, gravity is only around 0.08 meters per second squared. In such a low gravity environment, the experience of falling would be completely different. So the question becomes, if you were standing on that edge, would jumping actually be as dangerous as it seems? Or would the physics of this tiny world change everything? You would begin your descent very slowly at first. On Earth, after falling a certain distance, you eventually reach what is known as terminal velocity, where air resistance balances the pull of gravity and your speed stops increasing. In a stable position, this is around 200 kilometers per hour. But without an atmosphere, there is nothing to slow you down, and Earth's strong gravity would cause you to hit the ground extremely fast. Miranda. however, has no atmosphere at all. This means there is no air resistance to limit your speed. Even though the fall begins gently due to the moon's weak gravity, your velocity will continue to increase the entire way down, with nothing to slow you except the surface waiting below. Rupes, the massive cliff on Miranda, rises to about 20 kilometers in height. Such an enormous structure can exist because Miranda's gravity is too weak to pull it down into a smoother shape. We do not fully understand how this cliff formed. Miranda is likely too small to support plate tectonics like Earth. But one theory suggests that water beneath the icy crust froze and expanded, forcing the surface apart and creating enormous canyons stretching for hundreds of kilometers. With gravity on Miranda at just 0.08 meters per second squared, the fall would take much longer than you might expect. From the top of Verona Rupes, it would take around 12 minutes to reach the bottom. This changes the scenario entirely. It is not a sudden drop, but a long, slow descent through space. However, by the time you reach the bottom, your speed would have built up significantly. Without any atmosphere to slow you down, you would still be traveling at roughly 200 kilometers per hour. A parachute would be useless. But other methods, such as propulsion or cushioning, might offer a chance of survival. And from this extreme scenario, we move to another extraordinary world, Triton. The largest moon of Neptune is one of the most unusual objects in the solar system. Despite its significance, it has only been visited once. During a brief flyby by Voyager 2 in 1989, that single encounter, however, revealed a world unlike any other. Triton is one of 14 known moons orbiting Neptune. Some of these moons follow regular, circular orbits aligned with the planet's rotation. But Triton is very different. It follows a retrograde orbit, moving in the opposite direction to Neptune's rotation, and it is tilted at an angle of about 130 degrees relative to the planet's equatorial plane. Although its orbit is nearly circular, this unusual motion strongly suggests that Triton did not form alongside Neptune. Instead, Triton is believed to be a captured object, most likely a dwarf planet from the outer regions of the solar system. In fact, it accounts for about 99.5% of the total mass of all objects orbiting Neptune. In terms of size, Triton is the 7th largest moon in the solar system and is even larger than Pluto. This is significant because Pluto is often considered one of the largest objects in the Kuiper belt, suggesting that Triton may have originated from the same region. Evidence supporting this idea comes from observations showing that Triton and Pluto share very similar compositions. Both have surfaces dominated by nitrogen ice, along with smaller amounts of water, ice, and carbon dioxide. Their terrains are relatively smooth, with variations in elevation rarely exceeding 1 kilometer. Voyager 2 did observe features such as ridges, troughs, plateaux, and vast icy plains. But one of the most surprising discoveries was the lack of impact craters. This indicates that Triton's surface is relatively young and is being actively reshaped. Some regions also display reddish coloration, which is believed to be caused by methane reacting with ultraviolet light to form complex organic compounds known as tholins. While these compounds are not evidence of life, they are important because they are part of the chemical processes that can lead to life under the right conditions. Beneath the surface, Triton is thought to have a rocky and metallic interior, giving it a relatively high density of about 2 grams per cubic centimeter. This internal structure suggests that, despite its cold and distant environment, Triton may still possess interesting geological or even potentially habitable conditions deep below its frozen exterior. Triton is massive compared to the other moons orbiting Neptune. containing more mass than all the smaller moons combined. The radioactive decay within its rocky core may generate enough internal heat to drive convection in a subsurface ocean. Similar to what scientists believe exists beneath the surfaces of Europa and Enceladus. Like those moons, Triton appears to be geologically active, with cryovolcanism playing a key role in reshaping its surface. Instead of molten rock, Triton's eruptions involve water and other volatile materials. Liquid from beneath the surface rises and spreads across the landscape before freezing, much like lava on Earth, but in an icy form. This process continuously renews the surface, which explains why Triton has so few impact craters and appears relatively young. Some regions resemble vast, flat plains surrounded by raised edges. Structures known as paterae, which are thought to be the remnants of frozen cryovolcanic lakes. In some cases, central depressions or collapsed regions can be seen, marking the locations where material once erupted and later subsided. These eruptions may also transport minerals from the subsurface ocean up to the surface, possibly contributing to the presence of organic compounds such as tholins. If these materials originate from deeper layers, it raises the possibility that Triton's interior could contain the chemical ingredients necessary for life. Long fractures and linear features can also be observed across the surface, likely formed by tectonic stresses or freeze-thaw cycles within the icy crust. Images from Voyager 2 reveal additional evidence of recent activity. Dark streaks stretch across the surface in long, narrow patterns, sometimes extending up to 150 kilometers. These features are thought to be deposits from plume eruptions. Some of these plumes were observed reaching heights of around 8 kilometers. But unlike the powerful jets of Enceladus, they are likely driven by a different mechanism. One leading explanation is a solid-state greenhouse effect. Sunlight penetrates a translucent layer of surface ice and warms darker material beneath, such as tholins. This causes subsurface ice to sublimate, building pressure until the surface fractures and releases a plume. The erupted material then spreads across the surface, forming the dark streaks observed from space. A similar process has been identified on Mars, where carbon dioxide ice traps and releases gas beneath the surface. This process is only possible because Triton has an atmosphere. Although it is extremely thin, the surface pressure is about 0.014 millibars, comparable to conditions found at roughly 80 kilometers above Earth's surface. Like Pluto, Triton's atmosphere changes with the seasons. As temperatures rise, nitrogen ice on the surface can sublimate, temporarily thickening the atmosphere. Despite its thinness, the atmosphere is capable of supporting weather. Voyager 2 captured images showing clouds forming above the surface, and the consistent direction of plume deposits suggests the presence of prevailing winds. Triton's atmosphere also appears hazy, likely due to hydrocarbons that have not yet been fully transformed into more complex organic compounds by ultraviolet radiation from the sun. All of these processes working together: cryovolcanism, seasonal ice cycles, atmospheric dynamics, and organic chemistry, make Triton an incredibly dynamic world. In many ways, it behaves less like a typical moon and more like a captured dwarf planet, likely originating from the same distant region as Pluto. Triton stands as one of the most unusual objects in the solar system, a frozen world, constantly reshaped by hidden energy beneath its surface, holding clues not only about planetary formation, but perhaps even about the conditions that allow life to emerge in the most unexpected places.